Okay, assalamu alaikum. Welcome back. And today we are talking about, we're doing a quick review on describing motion and forces. So hopefully this review is going to be useful as well for the quiz that's coming on Tuesday. So get ready. It's going to be a short review. I know you like short reviews, so it's going to be straight to the point. But have your pen and paper ready and let's do some quick revision. Okay, so we're going to be describing forces, motion, and forces. First of all, what is this concept about a reference point? A reference point is basically a place that we have in mind that we look at, and then we know that the object is in motion because of it. So, for example, is this pen moving? Now, you might decide that this pen right here isn't moving, but then if I do that, it's moving. How do you know it's moving? Well, because my face is here, and my face is not moving, it's stationary. That means it's not moving. And then the pen is moving relative to my face. So my face becomes the reference point. It's the point of reference, the point of comparison. That's what a reference point is. It's a point at which to compare if something is moving or not. Okay? So we could look at a tree. So the tree, for example, over here could be a reference point because the car is moving past the tree. Or it could be another car. Okay? So for example, if I'm driving down the road, okay, and I'm looking at the car next to me, and there's a difference between us, then that could be a reference point to my driving. Okay, so it could be that I'm driving faster. How do I know? Well, it's my reference. The car next to me is going behind me, so therefore I'm driving faster than it. Okay, or I could just be standing on the side of the road and watching some cars, and I see the car whiz past me. I could be the reference point, or I could see it go past another car, and that could be the reference point. So it's just any point, a place, or whatever that can be used to compare and determine if something is in motion. That's basically it. So what is a reference point? It is a place or an object used for comparison, to compare, that is to contrast between 2 points, to determine if something is in motion or not. Okay? So I could say, for example, I could argue that as I'm sitting in front of you now, I am in motion. That means I'm changing my position. That's what in motion means. You're changing your position. How am I changing my position? I'm sitting right here. Well, I'm not changing my position relative to the wall behind me. I am not changing my position in comparison to the chair or in reference point to the desk or anything like that, but I am changing my position relative to the sun. So if I use the sun as a reference point, then I'm certainly changing my position because the earth is moving around the sun and I'm moving with the earth, right? So it's a bit like saying you're in a plane and the plane is moving in the sky and it's moving at constant speed, so you're not feeling any forces, you're not feeling any acceleration, and you're sleeping, and then you suddenly wake up and then you have a meal and then you go back to sleep. You don't feel anything, right? Even though you're flying and you're moving at a very, very high rate. You could be moving at 1,000 meters per second. But then what's happening is you're not feeling any of it. Well, somebody outside the plane could be looking at you and going, that person is moving very fast. But what about the person next to you? What about the person sitting right next to you on the plane? Now they're going to look at you and go, well, actually, you're not moving at all, right? So it depends on the point of view. It depends on the viewer. In this case, reference point really makes a difference. So reference point is anything that can be used to compare and contrast or to determine if an object is in motion. Right. How do we represent forces? We represent forces using arrows. So here's an example. We have an arrow pointing upwards, an arrow pointing downwards. So this force pointing downwards is called the weight force. Weight force. Okay, now sometimes in books you'll see it referred to as gravitational force. I don't like that because, well, gravity is not really a force, it's a field, and it results in a force which we call the weight force, which is a pull force towards the gravitational field. But gravity is a field. But anyway, for all intents and purposes, gravity is also a force. So as far as you're concerned in grade 8, gravity is a force, weight is a force. When you get to grade 11 or grade 12, then we'll have this discussion in a bit more detail. But for now, gravity is a force, weight is a force. Okay, so we have weight force acting downwards, or gravity, okay, gravity right? So gravity or weight, that's the force that pulls everything down. What is the force acting upwards? What is the force stopping things from falling down? Like, for example, I'm sitting on the chair and the chair has to be putting up a force, right? I mean, gravity's pulling me down and the chair is carrying my weight. Carrying my weight means that's a normal force, okay? So it is applying a normal force. And the reason why we call it a normal force is because it's perpendicular. It acts at 90 degrees, okay? It's normal force because it's perpendicular to the surface, and it is parallel and opposite to the weight force. So the weight force acts downwards, the normal force acts upwards. Then we have the push force on this side, pull force on the other side. That's just an example. This could be a pull force as well. And friction just means the force that exists between two surfaces that are in contact with each other. Okay, so for example, if I take my two hands and I rub together, that is friction, and it feels a bit warm as I start doing that. It feels really warm. That is friction force, and friction results in heat. Okay, another example of friction force, one that you're probably familiar with, is air resistance. Okay, so if I just blow gently on my hand, I can feel the air against my hand. Now that is actually a form of friction. It's the air particles in contact with my hand. So that is friction as well. Water, what about water? What about a boat going through the water? That is also friction because it's two surfaces that are in contact with each other. The water and the boat, they're in contact with each other, and the more water particles that the water goes through, that the boat goes through, the more friction it's going to experience. So we call that all sorts of things like water resistance, air resistance, and then, of course, friction has different types. There's rolling friction, fluid friction, kinetic friction, also known as dynamic friction or sliding friction, static friction. But you don't need to worry about any of that. All you need to know is that friction is the force that exists when two surfaces are in contact with each other. They must be touching each other. Must be. And even in the case of air, because you might be thinking, well, how is air friction? Well, air is still having to touch you. Or if, say, for example, a plane is going through the sky and air is hitting the plane, that is still air resistance. The air particles have to touch the plane, so therefore they're in contact with the plane. Okay, so all of those are resistance. The other way we represent forces is with a direction. So this one is acting down, this one is acting to the left, this one is acting to the right, and this one here is acting up. So the forces can be represented using arrows, and the arrows tell us a lot of information. The arrows tell us the direction of the force as well as the size of the force. So if I do this, for example, that is a big force acting south-west. Okay, but you don't have to worry about south or west or anything like that. You can just tell me left, right, all of that. So that's a big force acting left and down. Okay, what about this force here? That is a small force acting down and to the right. That is a medium-sized force acting up, and so on and so forth. Let's go to the next one. What are the different types of forces? Well, it turns out we do have different types of forces, right? So what are they? Well, we've got two. Let's do a bit of a mind map. We've got contact and non-contact forces. Non-contact forces. So basically what this means is if they are touching each other, they are contact forces. Touching, contact. Touching. Okay? And if they are not touching each other, not touching, then they are non-contact forces. Okay, so let's go to contact forces. What can be a contact force? Well, could be a push or a pull. Like if you push something with your hands or you pull with a rope, okay? Could be like tension. What else could be a contact force? Friction is certainly a contact force. What else could be a contact force? So we could say thrust, for example. Let's just stop there. I think that's enough. There's many different types of forces, including twist and lift and air resistance and all of that. But we're just gonna stop there. Non-contact forces. We've got examples like gravity, what I like to call weight, Weight is an example of a non-contact force, so gravity or weight. We've got magnetic forces, so magnetic attraction, magnetic forces. So not necessarily attraction, also repulsion. So if I have north and north, then they repel each other. North and south, they attract each other. And finally, electrostatic forces as well. Electrostatic forces. Electrostatic forces. And those are the forces that exist because of leftover electrons on materials. And so electrons left on objects can build up. And when they build up, other electrons on other materials, which have a negative charge as well, will repel those electrons. However, if the other material doesn't have a lot of electrons, then it's generally speaking polarized, which is positively charged, and something we talked about in the classroom. And then this object, which is negatively charged, will be attracted to the other one. So 3 different types of non-contact forces: electrostatic forces, magnetic forces, and gravity. And at this stage, I want to say you don't have to explain these. You don't have to worry about explaining these. You just have to be aware of them. So we just want you to know that there are electrostatic forces, magnetic forces, and gravity. And there is friction force, which exists between surfaces, tension, pull, push, that kind of thing. But we don't worry about you explaining each one of these. Right, what is net force? So net force is the overall force that an object experiences after all the forces are accounted for or added together. So it is the overall force acting on an object after all the forces are accounted for or added together. Accounted for just means added together, added, subtracted, whatever we need to do. So I'll show you examples of that. So for example, we need to work out the net force here. So over here we've got 4 newtons to the right, 4 newtons to the left. So the net force is going to be 0 newtons. And there's no direction in this one. So if we ask for the direction, we just say none. There's no direction here. It is because, well, it's not going anywhere. It's stationary. So you can say it's stationary, or you can say no direction. What about over here? We've got 7 newtons to the left and 2 newtons to the right. So overall, it's going to be 7 minus 2, which is going to be 5 newtons to the left. Okay, so the net force, F net, is equal to 5 newtons. Direction is equal to the left. What about over here? We've got 6 newtons to the left over here. 6 newtons to the left, 3 newtons to the right. So that means it's going to be, overall, it's going to be 3 newtons to the left. 3 newtons to the left. And that is, so the F net, the net force is going to be 3 newtons. And the direction is left. Okay? And over here we've got 7 newtons to the left, 4 newtons to the right, and another 4 newtons to the right. So that means we've got 8 newtons to the right, 7 newtons to the left, 8 newtons to the right, 7 newtons to the left. So it's overall F net equals 1 newton, and the direction is to the right. Okay? And that's how you solve that one. And of course, forces are measured in newtons. Hey, that is all from me. Good luck. All the best. I will see you on the next one, inshallah. Where's the mouse? It's gone.